lesson in the electricity unit. And before I begin, I just want to go back to the Google Classroom, and you'll see for this lesson 2, there is also a Google Doc which you can open. It'll look like this. You'll be able to go to File, make a copy so you can make your own, and you'll be able to fill in everything here. Okay, there's also another video that you should watch before this. It goes into a little bit more of the science aspect, as well as having some better animations than I was able to produce. Okay, so let's get into this. So, electricity, lesson 2. We're going to be talking about electrical current today. Okay, so electrical current. Okay, the symbol, if it's in a formula, is I, and I'll be talking about that in a second. The unit is in amperes or amps, and that can actually just be shortened down to a capital A. So if something had, say, 5 amps of current flowing through it, you could write it as just 5 and then capital A. Okay. What is current? Current is the amount of electricity flowing through a circuit or material. So when we talked about voltage, we used the metaphor of water flowing through a pipe. Okay. Voltage was the pressure pushing that water through. Okay. Current is the amount of that water flowing through that pipe. So the more electricity flowing, that means the more current is flowing. Okay. And it was named after Andre Marie Ampere. And that goes back to the symbol being I. A lot of people are saying, well, why is the symbol I? Why not A for amperes or C for current? And the reason behind it is actually because the original person that found it, okay, was French. And in French, he called it the intensité de courant. So I stuck. Okay. Every device is designed to handle a certain amount of current. Okay, so each has a rating that it can handle. And if you try to force too much current through something, it can fail or even catch on fire. So, very bad day. Okay, so AC versus DC. Okay, so DC is direct current. Okay, and that's where the current always flows in one direction. So it flows from positive all the way to the negative. Okay, so it's a continuous flow, one direction. And nearly all electronics use DC. So your video console, your cell phone, anything really that has electronics inside of it uses DC. And batteries supply DC current. That's why you can just put batteries into pretty much anything that's portable because it uses that DC current. And this is also why you need an adapter to plug in any of your electronics to charge them. So whenever you go to charge your phone, okay, you have a cord that goes from your phone and it goes into an adapter before it plugs into the wall. Okay, and that's because with alternating current, okay, the electrons change direction 60 times each second. So you can see here they're changing back and forth, and this is what's actually in your wall outlets. Okay, so in the U.S. it changes direction 60 times every second. Okay, over in Europe it's 50 times. And this is what comes out of power plants and through your home outlets. So everything from the power plants through the electrical lines all the way to your house and into your outlets is all AC. Okay. So if you tried to plug in something that needs DC into just an outlet with no adapter, it would fry. Okay. Controlling current. Okay. Resistors are used to limit the amount of current in a circuit. And if you're wondering, here's a picture of a resistor right here. Okay. There are a couple different forms, but this is one that's very common. And they're found in every electronic device. And if you're wondering what those little colored bands mean, okay, that actually will tell you how much resistance it has. So there's actually a table where you can look up, okay, if the first band's brown, second band black, third band red, and then over here gold. It would tell you exactly how much resistance that had. Okay. Now, fuses and circuit breakers are used to protect circuits in case too much current starts to flow. So fuses, one-time use. okay, and they burn out, and then you'd have to replace them. So over here we have some pictures. This is a fuse that you'd see maybe in a car. Okay, this is something you'd see in some electronic devices, and here's a larger one that you might be able to see in a home. So if you have, say your home is older, you might still have some fuses. Okay, more modern homes, newer built, okay, they have circuit breakers. And the nice thing about circuit breakers is they don't have to be replaced every time they trip. So you see that there's actually a little switch here, and that will let you flip it back on. So if too much current starts to flow, okay, it trips it and stops the flow. Okay, current versus power. Okay, the power, that's letter P, in a circuit is calculated by multiplying the voltage, which is V, of the circuit by the current, which, as we talked about, was I, in a formula that's just the power is equal to the voltage times the current. It's a pretty simple formula. Okay, the power and uses the letter P in any formulas, and the unit is actually watts. And the unit is named after James Watt, who was a Scottish engineer. Um, and your electricity bill each month is calculated in kilowatt hours. So we discussed what the prefix kilo means. It means 1,000. So how many 1,000 watt hours you use. So if you used 1 kilowatt continuously for a day is 24 hours. That would be 24 kilowatt hours. Okay? And that's how much the electric company bills each home. Okay, some sample current and power. Okay, so if you have 1 electron flowing per second, that's pretty much the smallest amount of current you could possibly have. That would actually be 160 times 10 to the minus 21. So that would be 21 zeros before it, and that would be 160 zeptoamps. So you'll probably never see that prefix again, but the prefix of zepto uh, means uh, 1 over 1 with 21 zeros. Okay, so a portable hearing aid. Okay, so these use 700 microamps, so that's 700 millionths of an amp. Okay, and it makes sense because these have to be pretty low power. Okay, the batteries that power these, they have to last a long time, and you can't just keep replacing them every hour or so. And if you're wondering about the power, it's one, that little m means milli, just like a millimeter, okay, or a milligram, 1 milliwatt. So that's 1/1000th of a watt, because the battery is only at 1.4 volts. If you're wondering how we got that number, 1.4 times 700 microamps gives me 1 milliwatt. An LED, or light emitting diode, okay, those use 20 milliamps. Okay, so that would be 20 thousandths of an amp. And the voltage is usually around 3 volts. So 20 milliamps times 3 volts gives us that 60 milliwatt rating for the amount of power that they use. So still pretty small. Now, an incandescent light bulb, these are the old-fashioned light bulbs. Okay, so these use, I'm just using a 60 watt as an example. Okay, that would use 500 milliamp or half an amp. Okay? And they run straight from your electrical wiring in your house, 120 volts. So 120 times half an amp gives us that 60 watt rating. Okay. Now, vehicle headlights also say 60 watts. These use 5 amps of power. And you might be wondering, well, if they're both 60 watts, why does this use so much more current? Okay. And it's because the voltage in your car is only around 12 volts, not 120 like in a house. So the 12 times 5 gives us that 60 watts. And this is why if you leave your car off with the headlights on, it can run down the battery pretty quickly. Okay, a toaster. Okay, these use about 16.7, each model varies a little bit, amps. And since these, again, run straight off an outlet, no adapter, it takes that 120 volts. So that 120 volts times 16.7 gives us 2 kilowatts or 2,000 watts. Okay, and this is why if you have a toaster plugged in and something else on the same circuit, it can trip that circuit breaker pretty easily because it's using a lot of power. Okay, some common circuit breakers. Okay, 15 amp or 20 amp. Okay, so you can see that toaster would automatically trip a 15 amp one. Okay, and these can range from 1.8 kilowatts to 2.4 kilowatts at 120 volts. So if you have, well, everyone has a fuse box or circuit breaker in their home. You can ask your mom or dad to show you, and you'll see something like this. Or if it's fuses, it'll be similar, but instead of circuit breakers, they'll be fuses. Now, if any of you guys are gamers out there, if you have any high performance PC graphics cards, okay, those can use a lot of current. They have the 24 amps, and that's because the voltage inside your computer is low, about 12 volts. So it needs that much current to get that much power. So 24 times 12 gives us that 288 watts. And obviously, different models will vary a little bit higher or a little bit lower, but all of them use a lot of current. Okay. Now, an electric oven. So if you have a propane oven, obviously it's different, but if you guys have an electric oven at home, okay, they use a lot of current because they have to heat up a large amount of space and keep it hot. So these are actually usually run at 240 volts. Okay, so they actually have to have a double circuit breaker in the box. So that 33.3 amps, okay, that was more than the standard circuit breakers. So an electric oven will actually be on its own circuit and have its own high current circuit breaker. So 33.3 times 240 volts gives us up to 8 kilowatts or 8,000 watts. Now, the supply to a welder. Okay, welders are usually run at 240 volts. Sorry, that got cut off a little bit. And you can see the plug here. Okay, it looks a little bit different. And that's because it's a plug for a 240 volt outlet. So those outlets are different, so you don't accidentally plug one thing into another. And they can take 25 to 50 amps. And usually, if you have a welder at home, say your mom or dad has a shop, they'll actually have their own circuit breaker as well because they use so much current. Now, the supply from a welder. So the welder takes that 25 to 50 amps at 240 volts, and it lowers the voltage while increasing the current. Okay. This is how you can get very, very high amounts of current flowing to be able to melt metal. Okay. And high voltage transmission lines. Okay, so those can handle up to 1,000 amps, each one of those little lines. Okay, and those lines look thin, but if you were actually zoomed in on them, they would be over an inch thick. So it needs that size in order to carry that much current. Okay. Lightning. Lightning can carry 30,000 amps. Okay, and we discussed previously what the voltage was. We said around 100 million volts or 100 megavolts. So that would be 3 terawatts of power. Okay, so they use a lot, they release a lot of power in a small amount of time. And some people usually ask, well, if they have so much power, why aren't we harnessing that to power our homes? And people actually have tried to do that. The main hurdles is that it releases all the energy in such a small amount of time. There's no battery that could charge that quickly. And even though it's 3 terawatts, it's only for a millisecond. So if we were to look at the entire amount of energy, it wouldn't be that much. Lastly, I included this, the Sandia Labs Z machine. Okay, and if you're wondering what this is, The Z machine is a experimental fusion reactor uh, that is at Sandia Labs here in the US. And they actually use 192 high-powered lasers to compress a pellet of hydrogen in order to fuse it into helium. And in order to run this, they have to use 70 mega amps. So that's 70 million amps. Okay. And they use a voltage of 24 megavolts. Okay. So every time they fire this, it releases 1.68 petawatts. So if you're wondering how much that is, I've written it down here. So it's thousand, million, billion, trillion, quadrillion. So 1.68 quadrillion watts. And if you're wondering, well, does that affect the power grid at all using that much power? And the answer is it would if they were just drawing power straight from the electrical grid. What they do is that they actually charge up a battery and capacitor bank. So that way they draw a little bit of power for a long amount of time. And then when it's all charged up, then they can fire and it won't affect the electrical grid. Okay, and that's the end of this. So try to fill in that sheet, and when you're ready, you can try to fill out the quiz.